Our session is the second of two on financial math. In this session, our math will get more complicated and our applications more interesting. We cover 5 topics. The first is compounding of both interest accumulation and discounting. The second is the present value of a stream of cash flows. The third is the concept of perpetuities. The fourth is the concept of annuities. And the fifth is the distinction between real and nominal interest rates and discount rates, and accounting for inflation. We start with the present value formula that we introduced in the last session. Note that we have replaced the designation FV, or future value, with C in the present value formula, so that now C sub T designates cash flow in year T. In the session 2, we had the example of a $100 cash flow occurring 1 year from now, and our interest was in calculating the present value of $100 that we would receive 1 year from now, and we determined that that present value was $89.29. Now we can calculate the present value of any cash flow at any time in the future using compounding. We'll start with the simplest version of compounding, which is annual compounding of interest. If we have a present value amount that we're investing right now, and we invest that dollar amount for 1 year, at the end of 1 year we'll have the present value times 1 plus R in terms of future value. But if we then allow both the interest that we've accumulated and the original principal to continue to be invested for a second year, we'll have this amount, which is the future value at the end of year 1, times 1 plus R for 1 more year in our interest accumulation process. So we'll have a future value at the end of 2 years, which is equal to the original amount invested times 1 plus R times 1 plus R again. That expression can be rewritten as the future value at the end of 2 years is equal to the present value times 1 plus R raised to the power of 2. Now we can generalize that expression for 2 years into an expression for an unlimited number of years so that we have the future value at the end of T years is going to be equal to the present value times 1 plus R raised to the power of T. Finally, we can solve this present value, future value expression for the present value. So the present value of any cash flow that might occur at the end of T years is that future value divided by 1 plus R raised to the power of T. Now let's take an example. What is the present value of $100 received 2 years from now if the discount rate is 12%? I scooted over to our Excel file to a worksheet that I've labeled the present value 2 years. And I've entered our parameters: the discount rate of 12%, the term of the discounting process, 2 years, and the future value that we expect to receive at the end of 2 years of $100. Here's our presentation of the stream of cash flows. Again, we want a column that is labeled year end, and now we need to extend our time series from year 0 to year 1 to year 2. The cash flows that we expect to receive in these years are nothing in year 0, nothing at the end of year 1, and at the end of year 2, we expect to receive $100. You can see I've already calculated the present value using the NPV function in Excel as $79.72. Let me delete that answer and again go to the function wizard, find the NPV formula, invoke that NPV formula, which now again has the arguments, the rate, the discount rate that we're going to use, highlight the cell with the 12% discount rate in it, and the cash flow values that we're going to use. Now, what we're going to do here is something a little bit different from what we did when we were calculating the present value after 1 year. This box or this argument in the NPV function requires that we highlight the cells containing the cash flows beginning at the end of year 1 and going out to the term of the cash flow sequence that we're interested in evaluating. So what we're going to do is to first to click on the cash that occurs at the end of year 1, and then hold the left mouse button down and drag the cursor down to the cell that contains the cash flow at the end of year 2. And now we've highlighted a stream of cash flows that include the cash flow in year 1 and the cash flow in year 2. And we're finished. We can say now, okay, we have completed the calculation of the present value of $100 received at the end of the second year. Instead of using the NPV function in Excel to calculate the present value, we could have used the present value table. So now we're looking at the present value table that we're familiar with. And recall from the last session that we were looking at a 12% discount rate and a 1-year period, and we used the discount factor of 0.8929 to calculate our present value. In the new situation, we're still using 12% as our discount rate, but we're using 2 years as the period of our interest in terms of our discounting process. And we can pick up the new discount rate that we would apply using the table of 0.7929, and we could take that number, multiply it by $100, and arrive at our $79.72. I've gone back to the present value table to kind of reinforce the present value concept that we're trying to develop right now. Again, I want to note that in general you're going to be using the NPV function in Excel to calculate present values. But what this table allows us to do is to see that, let's hold our discount rate at 12%. And now we've noted that if we have to postpone receipt of the $100 for 1 year, the present value is $89.29. If we have to wait 2 years, the value of $100 to us after 2 years has fallen to $79.72. And you can see if you just kind of scroll down this column, the longer you have to wait to receive $100, the lower the value to you of that future cash flow. And so, for example, if you have to wait a full 10 years to receive the $100, the value to you of that expected receipt of cash is only $32.20. Another relationship I want to point out is the relationship between the discount rate and the present value. We can use that. We can see that using this table as well. So let's stick with our 2 years as the length of time we have to wait to receive our $100. If our discount rate is 12%, or if we can, another way of thinking about it, if we can earn 12% on our money, then the value of the $100 in 2 years is $79.72. But if our discount rate is only, let's say, half of that, or 6%, then the present value of $100 received 2 years from now is $89. Notice that the lower the discount rate, if we kind of scroll to the left in this row, the lower the discount rate, the higher is the present value of any future cash flow. Very important principle, and it kind of goes to a relationship that we're going to talk about later on in the course. Firms have an interest in minimizing their discount rates. A firm would much prefer to have a discount rate of 6% over a discount rate of 12%. Because if a firm can borrow money at 6%, the value of its future investments is going to be significantly higher than if it has to pay 12% to borrow funds. In the previous slide, we covered interest accumulation and discounting for annual compounding. Using the expression in the previous slide, we can calculate the future value of any present investment compounded out over any number of years, and we can then reverse that and calculate the present value of any future cash flow out over any number of years. On this slide, we're going to make things a little bit more complicated by covering compounding that occurs more frequent than annually. So let's start with more frequent than annual compounding of the interest accumulation process. Here's our formula for the future value of an investment that could be compounded more frequent than annually. Notice that we've added a term M that appears twice in this formula. First we have M, and let's let M represent the frequency within a year in which we have compounding of interest. As an example, just kind of a working example, let's say that we're dealing with quarterly compounding of interest. In that case, M is 4. So we have the future value is being equal to the present value times 1 plus the discount rate divided by 4, raised to the power of 4 times the number of years that we are going to be having our investment. So once again, as an extended example, let's say that the interest rate we can earn on our money is 8%. We have quarterly compounding of interest. So this expression actually effectively calculates the interest rate that's earned per quarter. So 8% divided by 4 gives us a 2% rate of return per quarter. But we're going to get to compound that 2% for 4 quarters, because the expression, the exponential expression, is M is 4, and let's say T is 1 now. So we're going to raise that to the power of 4. We can solve the future value formula, just as we did in the previous slide, for the present value of some future cash flow that we expect to receive out into the future, even if we have more frequent than annual compounding. Let's take an example to see how more frequent than annual compounding can affect our calculations. The example is, what is the value in 1 year of an investment of $100 at 8%, compounded annually, quarterly, and daily? I've moved over to our Excel file to show how to calculate future values with more frequent than annual compounding of interest. I've labeled this worksheet Compounding of Interest within 1 year. Here are the parameters that we're interested in using. We have an interest rate of 8%. We have a term of 1 year for our investment, and we have an initial investment amount of 100. Over here, I've indicated the frequency of compounding or values that we want M to take on in our future value calculation, where M is 1 for annual compounding of interest, M is 4 for quarterly compounding of interest, and M is 365 for daily compounding of interest. Now, I've already calculated the future value amounts for annual, quarterly, and daily compounding of interest in these 3 cells. But what I'm going to do now is to delete these calculated amounts and recalculate them to show you how to do it. We're going to write in a new future value formula, just like we did in the previous session. Future value is equal to the present value times, open parentheses, 1 plus, highlight the cell with the interest rate. Now we're going to have to divide that interest rate by the frequency of compounding of interest. So I'm going to say divided by, and then highlight the cell reference with 1, with M equals 1. Close the parentheses, use the up caret to designate an exponent, and then indicate the exponential expression we want is M times T. So once again, I'm going to hit the cell reference for M times the cell reference for T. Let's hit enter now to see if we've calculated the right future value. We've calculated the future value of an investment of $100 at 8% with interest compounded annually to be $108. Now we want to see what the future value will be with more frequent than annual interest compounding. Before moving to those calculations, I want to show you a little trick in Excel that will allow us to do some calculations much more efficiently and quickly than if we didn't know the trick. The trick has to do with what's called anchoring of cell references. We go up to our formula bar and click on it. We're going to be able to edit or modify the formula just a little bit. What we're going to be doing is essentially copying the formula for future value that is in this cell, in the cell D4, over to the cells E4 and F4. We want to be able to copy that formula across rather than rewriting it every time. But when we copy formulas across from one cell to the next, the convention in the Excel function, in the Excel program, is to have the cell references move as well, unless you lock particular cell references. By cell references, I mean here on the formula bar, we have a B4, a B2, a D3, a D3, and a B3. Different cell references indicating where on the spreadsheet are the values that we want to put into our calculation. Some of these cell references, or essentially numerical amounts, we want to change as we go across, and some we want to stay the same. Okay, specifically, the cell reference B4, I'm going to click right before it here, the cell reference B4 indicates the initial investment. We want to lock that cell reference because we don't want it to move across the spreadsheet as we do this copy function. To lock the cell reference, right at the top of your keyboard, there's a key that's labeled F4. So if I hit F4, what I get is dollar signs in front of the B and the 4 in the formula. Those dollar signs can be considered anchors, and we've anchored that cell reference B4 so that we're not going to have it change as we copy across the spreadsheet. What else do we want to lock? We want to have now we're looking at the cell reference B2. B2 indicates our interest rate. That interest rate is also going to be locked because we don't want it to change as we go to more frequent compounding. Let's look at the next cell reference, D3. D3 indicates the frequency of compounding per year. We do want that one to change as we go from 1 to 4 to 365. So I'm not going to anchor that cell reference there or the D3 there. We're going to leave those unanchored. And finally, again, we want this B3, which is the frequency of which is the number of years over which we're investing. We want that to be anchored, so I'm going to hit F4, and you can see the anchors in front of those cell reference indicators. Hit Enter, and what we see is that our calculation of the future value for our $100 in investment at 8% compounded annually hasn't changed. We still have our $108 future value. But now we can highlight this cell again, put our cursor crosshair on the southeast corner of the cell, hold down the left button, and drag across to the cells where we want to enter our future values for the other compounding frequencies. I'm still holding down the left mouse button, and I'm going to let it up now, and what we get are the correct answers for our future values for quarterly compounding and daily compounding of interest. Just to see how the Excel program has worked, let's click on the cell E4 here, which is the future value for quarterly compounding of interest, and go up to the formula bar, and you can see what has happened is the cell references for the initial investment and for the interest rate and for the number of years over which the interest is compounded, they have all stayed the same. They're the same as they were in in cell D3, D4. Those cell references are all the same. However, what has changed is the frequency indicators. The cell designation E3 is correct for quarterly compounding of interest. Over here, we have D3 for annual compounding of interest, and then way over here, we have F3, that cell, for daily compounding of interest. A few key learning points here in this cell. One key one is that more frequent than annual compounding of interest increases the future value. So if we move from annual compounding of interest, what we get at the end of the year is $108. If we were to compound interest quarterly, we get $108.24. And if we were to break the year up into 365 days and compound daily, we would wind up at the end of the year with $108.33. A second point to note is that the advantage of more frequent than annual compounding occurs, the principal advantage, or most of the advantage, occurs moving from annual to quarterly. You get an additional 24 cents going from m equals 1 to m equals 4. Going from m equals 4 to m equals 365, you get only an incremental 9 cents in value. So most of the benefit of more frequent than annual compounding of interest occurs in going from 1 to 4 rather than going from 4 to 365. Finally, you can see the effective annual yield or the effective annual interest rate that the investor gets with different frequencies of compounding. For annual compounding of interest, I'm going to label this here effective interest rate. For annual compounding of interest, we get an effective interest rate of 8%. For quarterly compounding of interest, we get an effective interest rate of 8.24%. And for daily compounding of interest, we get an effective interest rate annually of 8.33%. Let's move on to the next complication in our financial math. Most of the investment opportunities that we'll consider in this course, or that your firm might face, or that you might face as an individual, involve cash flowing in each of several years in the future, or a cash flow stream. We want to show or consider how to calculate the value of a stream of cash flows, not just the cash flow in a particular year. Here's the general expression for the present value of a stream of cash flows. The present value is equal to the sum of the discounted cash flows associated with a particular investment over the term of that investment. So we start with, let's say, an investment that has cash flowing in year 1, year 2, maybe year 3, year 4, etc., out to a particular term. And we're going to use capital T now to indicate the term of an investment opportunity. So we have cash flowing, let's say, in each year out to the end of the investment opportunity. We know that the present value of cash at the end of a cash flow at the end of 1 year is equal to that cash flow divided by 1 plus r to the 1. And we've also seen that the present value of cash flowing at the end of year 2 is equal to that cash amount divided by 1 plus r squared. If we just have a 2-year investment, the present value of that 2-year investment is going to be equal to the discounted value of the cash in year 1 and the cash in year 2. But we can obviously extend our consideration to an investment that might last an indefinite number of years. And once again, our number of years, our term that we might be considering in the course for investment opportunities will run anywhere from maybe 3 years out to 100. The present value, then, of a stream of cash flows is simply the sum of each year's discounted cash flow. This is a shorthand representation of this general formula. Sometimes we see the present value of a stream of cash flows indicated as the sum from year or t equals 1 to the term of the investment of the cash in each year, little t, divided by 1 plus r raised to the power of t. That's just a shorthand expression that you may see in the book. You will see in the book, and you may see it elsewhere. So let's go to an example. What is the present value of an investment that allows us to have a stream of cash flows where the cash flow in the first year is $100, the cash flow in the second year is $150, and the cash flow in the third year is $165, if our discount rate is 7%. We're back to our Excel file. I've labeled this spreadsheet the present value of a stream of cash flows. Here are the parameters. The discount rate is 7%. The term of the investment is 3 years. And now I've indicated the stream of cash flows with our column year end and our column C for cash flow. We have a term of 3 years, so we start with year end 0, year end 1, year end 2, and year end 3. and the cash that we expect in year 1 is $100, the cash that we expect in year 2 is $150, and the cash we expect in year 3 is $165. So let's calculate now the present value of this stream of cash flows. You can see I've already done that, and the present value of the stream is $359. As usual, I'm going to delete that calculation and redo it going up to the function wizard again, finding the NPV function in the function wizard, saying, okay, yes, we want to use the NPV function. Once again, I want to highlight the cell with the discount rate. And now I want to highlight the cells with the stream of cash flows. And I'm going to start, as we need to, with the cash flowing in year 1 and go down to the cash flowing in year 3. And once again, I want to hold the left mouse button down and drag the cursor across or down this column so that we have the cash flows in all 3 years highlighted, and then release the left mouse button, and we see in the value box that we have the cash flowing, or the cell reference, B7 to B9. Okay, say OK, and we have our calculation of the present value of a stream of cash flows of $100 in 1 year, $150 in year 2, and $165 in year 3, and the present value is $359. Now let's just talk a little bit about the interpretation of that present value calculation. First, note that in raw terms, this investment generates $415 for us. But because we're not going to be getting that $415 right now, and in fact we're going to be waiting 1 year for this amount, 2 years for that amount, and 3 years for that amount, the value to us right now of this new business opportunity is less than $415 because of the time value of money. In fact, the value to us is $359, assuming that we can earn 7% on our money. Another way of looking at this set of opportunities is that we as investors would be indifferent between getting $359 right now or having the rights to receive a stream of cash flows that starts at $100, jumps up to $150 in 2 years, and goes to $165 in 3 years. We would be indifferent about those two business opportunities. You can see how very easily, mechanically, we can apply the NPV function in Excel to the calculation of the present value of any generally represented stream of cash flows for any term out into the future. All we need is a column here that indicates the number of years that the investment is, or the new business opportunity is going to last, a column here indicating the cash flows that are going to be spun off that business opportunity, and a discount rate. We have those, we can calculate the present value of any stream of cash flows for any period of time in the future. The previous slide presented the present value of a general stream of cash flows, or maybe more accurately, presented kind of a general expression for the present value of a stream of cash flows, where the cash flows can take on any values in the future. In the next few slides, we want to cover some special cases for cash flow streams. The first one I want to cover is the notion of a perpetuity, which is defined as a constant stream of cash flows forever. Now, it is a fact that you can purchase an investment instrument that gives you the rights to receive a constant stream of cash flows forever. You can purchase perpetuities from the government of the United Kingdom. And then you can sell those instruments in the open market You can pass that right, that perpetual right on to your heirs. You can do anything you want with it. And the government of the United Kingdom promises to pay you or your heirs or your assigns, that is, anybody else that you would sell this instrument to, a constant amount forever. Let's look at the determination of the present value of a perpetuity. Okay? We can think of, in general, the return on any investment as equal to the cash flow associated with that investment divided by the present value. Or kind of more generally, the interest that we earn on an investment is equal to the cash flow of that investment divided by the present value. This is really kind of a conceptual look right now. If we solve this expression for the present value, what we get is the present value of an investment that has a constant cash flow is equal to the annual cash flow, C, divided by R, the discount rate. In addition to perpetuities that are sold by the government of the UK and maybe even some other governments in the world, the notion of a perpetuity and the perpetuity formula is used in determining the value of stocks, particularly non-growth stocks, and in estimating the terminal value of in investment decision analyses that we're going to be doing. We're going to be covering both of these applications later on in the course, and so even without going into any examples right now, I'm going to just ask you to sort of hold your interest in perpetuities to the extent you have any for a bit longer. Okay, the next notion I want to describe is that of a growing perpetuity, which is a stream of cash flows that grows at a constant rate forever. The expression for the present value of a growing perpetuity is that you take the annual, or let's say the initial cash flow, divided by the discount rate minus the growth rate. The application of the formula for a growing perpetuity is in terms of the valuation of growth stock. Once again, we won't prove this or apply it yet. We'll come back to it when we get into stock valuation in the next session. The final specific cash flow stream I want to talk about is the annuity. An annuity is a constant stream of cash flows for a given term. Here is the expression for the present value of an annuity. And the good news is that there's no sense in memorizing this expression. Some of the other expressions that we've gotten in this math part of the course are really worth not really committing to memory, but to sort of having a good sense about. This one is not one of those. Rather, there are ways to calculate the present value of annuities that we're going to go into in an example in just a bit. But I want to make the note, first of all, that we use the concept of annuities and this particular formula as ways to determine the value or price of bonds that are traded in the bond markets, or the value of winning, let's say, a state lottery. And so let's move to that example to show how to use the concept of an annuity. The example is, what is the value of winning a $1 million lottery if the payout is in 20 annual installments? Now, those of you who've already won the lottery know that if you win $1 million lottery, you don't get $1 million right now. If you did get the $1 million right now, obviously the present value of winning the lottery would be $1 million. But all the states that I know of anyway pay out their lottery winnings over time. So that's the example that we want to use. And because they pay out the winnings over time, you can see that the present value of winning a $1 million lottery is going to be a lot less than $1 million because of the time value of money. We're back to our Excel file again. I've labeled this spreadsheet the value of winning a $1 million lottery. Now, the parameters that we have to doing this lottery valuation are first the cash flows that you get every year. And if you win $1 million lottery and they pay and the state pays you, 20 equal amounts of that $1 million, equal pieces of that $1 million, you're going to get $50,000 per year for 20 years as your cash flow stream. That is a 20-year annuity of $50,000 per year. Now, the determination of the discount rate here is pretty important. Let's say that the person who wins the lottery has a discount rate of 8%, which comes from where? Once again, think about where that discount rate might come from. It comes from either that person's opportunities for investment. So let's say the person is thinking he or she can earn 8% on his or her investments, or that person's rate of time preference for consumption. That is the extent to which the person, as a consumer, prefers to buy things now over things in the future. The 8% discount rate is an important determination of the value of winning the lottery, as we'll see when we do some more calculations here. So to determine or to calculate the present value of winning the lottery, or the value of winning the lottery, what we need is a column indicating the years over which the lottery winnings will be paid out. So you can see I have a year-end column, and I'm going to scoot down here and show you that it goes from year 0 to year 20. Okay. The next column over has the cash flows in each year, and we're going to assume that the state pays out the $50,000 at the end of each year, starting in year 1 and going out to year 20. So we have our 20-year stream of constant cash flows, which is the definition of an annuity. Now we want to calculate the present value of the annuity, and to do so, once again, we're going to use the NPV formula. And as usual, you can see that I've already calculated it to be about $491,000. Let's see how I arrived at that present value calculation. I'll delete that amount. Go back to the function wizard. Find the NPV function. Say, okay, that's what we want to use. The first argument in the function is the discount rate. And then the second argument is the cash flows for years 1 through 20. So I'm going to click the cell that indicates the cash flow in year 1, hold the left mouse button down, and drag the mouse down to year 20. Let the left mouse button up, and we have indicated now in this box that we want the cash flows in the cells D4 to D23. Say, okay, yeah, that's what I wanted, and we get the value of winning the lottery to us right now. Let me restate that. The value of winning a $1 million lottery, if the lottery payout is in 20 equal installments of $50,000 per year, and if our discount rate is what rate do we use? 8%. The value is $491,000. Again, interpretation. The lottery winner is indifferent between now getting paid $491,000 right now and receiving $50,000 per year for 20 years. Notice I've ignored taxes and everything, and we could build taxes in, but right now we're dealing with concepts, and I want you to see the concept. Indeed, for those of you who've won the lottery already, you know that when you win the lottery, you get phone calls from financial institutions that offer to pay you a given amount right now if you will essentially sell them your lottery rights. And now you can see how, for those of you who win the lottery in the future, how you should go about making that decision. The decision depends importantly on your discount rate. To make that point with an example, let's say that the person who won the lottery actually had a higher discount rate, which means the person had either a higher rate of time preference for consumption or opportunities for investment that were higher than 8%. Let's say that the person thinks that she has investment opportunities at 11%. So I'm going to replace the 8% with 11%. Hit enter, and then scoot down to the bottom of the worksheet, and you can see that the present value has fallen from about, what did we say, $491,000 all the way down. You've lost a whole $100,000 in value. And that's because the lottery winner is less willing to postpone receipt of the money if she can invest her money at 11% than if she can invest it at 8%. Just to make the point, one more example. Let's change the discount rate from 11% to an even lower rate. Let's change it to 5% and see what happens to the value of winning the lottery. You can see that the present value now goes up from about $491,000 all the way to $623,000. The person is more willing to postpone receipt of these cash flows because her opportunities for investment or her time preference for consumption are lower than let's say, the person with an 8% discount rate. The little trick that we just did of changing the discount rate and immediately getting a revision of the present value calculation was possible because we set up our NPV function with a cell reference. And that's one of the reasons why I always use cell references in the Excel functions that we're going to use. Using cell references, rather than, let's say, writing in here 8%, I use a cell reference that designates where 8% is. It allows me to change the discount rate and see what happens to the present value calculation. Before closing this session, I want to return to a concept that we introduced in an earlier session when we were talking about the determinants of the time value of money. The concept or process that I want to talk about now is inflation. Inflation affects our thinking about interest and discount rates. Indeed, inflation causes us to think about the distinction between real interest rates and nominal interest rates. Let's define a nominal rate as the interest rate that's stated on a financial instrument. Let's say a bank account says it pays you 4% interest these days. That is a nominal rate. We know a nominal rate a priori. We basically can say, oh, if I put my money into a bank account, I'm going to earn 4% interest on it. A real rate is a nominal rate adjusted for or taking out inflation. Real rates can actually only be known after the fact. So if you put your money into a bank account that pays a 4% nominal rate, you really don't know at the end, you won't know what your true rate of interest in real terms is until the end of the year when we figured out how much prices have risen, how much inflation has occurred. Now, there is a math relationship between nominal and real interest rates. This is the exact mathematical relationship, and you can look at it and see what you think about it. Essentially what it says is that 1 plus the real rate, let's say the real rate is 3.8%, times 1 plus the inflation rate, let's say the inflation rate is 6%, equals the nominal rate. And if you run out those numbers, you can see that it all works. In a practical sense, or a common approximation, a lot of people use this relationship, which is the nominal interest rates are approximately equal to real interest rates plus inflation rates. So if you think about if you have a financial instrument that says it pays you 10%, to find out what it really pays you after inflation, you want to subtract the rate of inflation from that 10%. And there it is there. The difference between the 10% and the 6% is going to be the real rate of interest that you earn after inflation. So we could actually solve this expression for real rates, and the real rate is equal to the nominal rate minus the rate of inflation. We're going to be using and actually highlighting the distinction between real and nominal rates in some of the analyses that we do in the future. In particular, what we want to do is to ensure that our cash flow analyses are consistent in their treatment of inflation, in terms of whether we're looking at nominal cash flows, that is, cash flows that include inflation, and if so, we want to make sure that our interest rates or discount rates include inflation, or we could have our cash flows free of inflation, and then we would want our discount and interest rates to be free of inflation as well. We're going to be coming back to several opportunities to understand this relationship more completely as the course progresses.